Thanks to the chairman for the kind introduction. Good morning, everyone. I'm Ning from MBEL's lab of Tianjin University. Today, I'm going to talk about the conducting polymer nanowire sensor fabricated by soft lithography for VOCS detection. And gas sensors fabricated with nanowires as detecting elements are powerful due to their many improved characteristics, such as high surface-to-volume ratio, ultra-sensitivity, faster response, and low power consumption patience. And very small amounts of gas can change the electrical characteristics of the nanowires. Up to now, so many kinds of nanowires have been fabricated with silicon, metal oxide, carbon, or conducting polymers. They have been used as building blocks for the gas sensors. And so the new nanowire gas sensor fabrication processes have been widely investigated by a lot of research groups. And there are many direct methods in fabricating nanowires. They are commonly classified into two categories. The first category is bottom-up approach. The significant advantage of the bottom-up approach is that they can be used to generate structures with dimensions ranging from angstroms to hundreds nanometers. However, patterning the required and orderly structure on specific location is particularly difficult for these bottom-up approaches. And also, it is difficult to fabricate two structurally similar devices. On the contrary, the significant advantage of the second category top-down approach is that the structures can be patterned and built in place so that no assembly step is needed. However, the challenges for all the top-down techniques is that while they work well at microscale, it becomes increasingly difficult in nanoscale dimensions. And also, these top-down techniques suffer from high equipment cost and complex fabrication processes. So, our lab for the first time reported on a direct nanomolding method, nanomolding in capillaries, to pattern multifunctional materials from their solutions at sub-100 nanometers. And this picture shows the whole fabrication processes of the NAMIC approach. First, a thin film of imprint resist T85 was being coated onto the PDMS substrate. After that, the composite PDMS substrate coated with T85 and the silicon template were inserted into the stamping machine. After the nano imprinter process, nano grooves were formed on the PDMS substrate. And this picture shows the SEM results of the nano grooves fabricated on the PDMS substrate with the cross-section of the imprinted polymer films. And after that, the PDMS mold was placed in contact with the substrate so that nano grooves form nanochannels. After the formation of nanochannels, a drop of p-PSS was placed at one end of the nanochannels. So the liquid fills the nanochannels by capillary action. After the solvent completely evaporation, the nanowires, the PDMS mold was gently removed from the substrate, leaving the nanowires on the substrate. From the SEM and AFM results, we can see that the p-PSS nanowires are successfully fabricated on a large area without obvious defects. And now, the major improvement is the use of hybrid nanomold with harder, more well-defined features, thus allowing accurate nanoscale surface patterning. NAMIC can create large area structures at sub 100 nanometer in a relatively short time, and it can be used to generate. It can be used to pattern a large variety of materials from the solutions, such as nanoparticles, biomoleculars, and conducting polymers. And NAMIC uses only simple materials and low-cost lithography techniques, thus providing a low-cost and efficient nanopatterning method. And the whole fabrication processes can be proceeded outside the clean room, which is accessible to most research labs. Okay, after the formation of the nanowires, the metal electrodes were formed on the side of the nanowires with thermal evaporation through shed mask. After that, the whole substrate was sealed into a package, the metal electrodes were well bonded to the connector. Thus, a fully resistive gas sensor is successfully fabricated. And the current voltage results clearly show that the resistive gas sensor has a good ohmic property. And to test the gas sensing performance of the resistive gas sensor, the sensor was used to detect different concentration of ammonia. And from the responses of the resistive gas sensor have no significant changes after exposed to the same concentration of ammonia, implying the good repeatability of the resistive gas sensor. And also, a comparison of ammonia detection using a nanowire gas sensor and the thin film gas sensor was carried out here. Due to the high surface to volume ratio, the calculated sensitivity is higher of the nanowire gas sensor is higher than that of the thin film gas sensor. All these results suggest that the resistive gas sensor fabricated by the NAMIC approach has a good gas sensing performance. And next, sensor array modified by different gas sensitivity materials is just like our olfactory cells. It captures the moleculars and produces unique identification code bars. When we compare the code bars with the known code bars in the database, we can determine the VOC type eventually. It is the Inno system. Due to the high surface to volume ratio, the nanowire gas sensor has become the promising candidate for the Inno system. So by using the NAMIC approach, we have fabricated a p-PSS nanowire sensor array Inno system. The Inno system includes non-functionalized p-PSS nanowire sensor and 4 other nanowire sensors functionalized with different kinds of gas sensitivity materials. And actually, the sensor response could be tuned by the introduced groups. And from the XPS result, we can see that the gas sensitivity materials have been successfully fabricated on the p-PSS nanowires. And with gas analyzer in analytical chamber, analyzer absorbed into polymer nanowires, and the resistance increased. By flushing with the natural gas, the analyzer dissolved immediately, and the sensor response recovered to its initial steady state. The changes in sensor response could be related to combinatorial effects of changes from the morphology, electronic state, and polymer structures. And also the reversible processes of the desorption to original state exhibit the good repeatability and stability of the Inno system. And here, since the nanowire gas sensor in Inno system exhibit different response for an individual VOC, the 5 cans nanowire sensors together compose unique identification code bars for different VOCs. And therefore, after creating a database for code bars of standard VOCs, the code bars of unknown VOCs will be generated by the inode system and compared with the known code bars in the database to determine the VOC type. And the signals obtained from the sensor response were also analyzed with the PCA after the signals were normalized to their initial values. The clear classification of 5 clusters related to different kinds of VOCs can be observed, enhancing the ability of the Nanowire gas sensor inode system fabricated by NAMIC approach to recognize and separate different VOCs. And at last, let's make a summary. A repeat and cost-effective soft lithography technique was used to fabricate the PSS nanowire without obvious defects on a large area outside the clean room. And second, the resistive gas sensor has been successfully fabricated and tested for ammonia at room temperature. And third, functionalization was applied for absorption analysis, which produced identification code bars. The Nanowire sensory inode system increased the selectivity and specificity of VOC detection. And here I would like to thank Professor Xuexin Duan for his kind guidance, thanks Jiang for his help, and thanks other guys in my lab, and thanks for this financial. You can get more information about our lab from the QR code or the website directly. And thanks for your attention. Thank you very much.